All right, let's get our attention up front. Eyes up here, everybody. Let's go ahead and get started going through our notes. So, starting off, let's talk about the theory that's going to help us explain like why everything that we're learning happens. Okay? So, to start off, the theory is called Vesper theory. Now, I know it's spelled Vesper theory, but we just call it Vesper theory. Now, what this actually stands for is valence shell, which we already know what that is, right? Valence, it just means the outer electrons. E then stands for electron. P stands for pair. And then R, our last word there, is repulsion. Okay? Now, if we break down what this means, is that if we have pairs of electrons in the valence energy level, so in the furthest out energy level, they repel each other. Now, from our last module, remember that all of our electrons, when we drew dot structures, ended up in pairs, right? They were either pairs that were bonding two atoms together or pairs that were just sitting alone on an atom, right? And so if we have those electrons, they're going to repel away from each other and get as far away as possible from each other. That's all this theory says. Now, if we actually read through the bullet points here, so electron pairs repel one another and arrange themselves as far apart from each other as they can get. Now, you can have electron pairs either as bonded pairs, so two electrons between two atoms, or you can have an electron that is not bonded. That we call a lone pair. So we have two vocab words buried in the slide as well, right? We have a lone pair and a bond pair. Questions so far? All right. So now let's look at an example here. So if we look at CH4 here, CH4 has a total of 4 bonded pairs because each pair is between two atoms. If we look at F2, we have 1 pair of electrons that is being shared. So there's 1 bonded pair, and there's 1, 2, 3, 4, 5, 6 lone pairs. And then lastly, in Ne, there's a total of 4 lone pairs, and there's no bonded pairs. All right? So when you look at electrons that are between two atoms, like these ones, these are called bonded pairs. All the ones that are not between two atoms, like all of these are called lone pairs. Questions so far? Yeah. Yes, so the red ones are the bonded pairs. Now I was going to get to that in a second. If you look down below here, it says lone pairs is the red color. It should be blue. We flipped it on accident. And then the bonding pairs, those are the red ones. So that's why I added the highlighting there, right, just so we can figure it out there. Okay, so all the ones highlighted in yellow, those are, I still flipped it. Jeez, sorry. So everything that is currently highlighted in green, those are the lone pairs of electrons. Everything highlighted in yellow, those are our bonded pairs of electrons. Does that make sense so far? All right, questions? All right. So now what I want you all to do is try and practice here. So I want you all to try and figure out how many lone pairs does each molecule have here? How many lone pairs does CH4 have? What about H2O? What about NH3? So go ahead and try and figure this out. How many lone pairs does each one have? See if you can do it.
So it means electron pairs that don't bond to another. Well, so all 3 of them, you have to put like a number, like 0, 1, 2, 3, 1, 3, for how many pairs?
All right, let's get our attention on me, please. Eyes up here. Let's get our attention up front. Eyes up here, please. Let's quiet down. All right. So we're looking for electrons that are not between two atoms. So if we look at CH4, every pair of electrons is between two atoms. So those are all bonded electrons. This one has 0 lone pairs. If we look at H2O, we have 2 pairs of electrons that are not between two atoms, right? So we have 2 lone pairs on water. And then if we look at NH3, in NH3, we just have 1 pair of electrons that is not between atoms. So we just have 1. All right, questions here. All good? All right, let's go ahead and continue. So now we're going to talk about molecule shapes. Now, one thing I want to warn y'all before we start. Not every single molecule shape is listed in the notes. Some of these you just found during your data collection. And so to figure out the names, you'll see to use what's listed in your data collection. Now, we're going to go over some of them, but not every single one, okay? Now remember, electrons are going to repel away from each other as much as possible. So if you just have 1 or 2 things attached, the farthest they can get away from each other is like in a straight line, 180 degrees apart. If you have 3 things attached, the farthest apart they can get is about 120 degrees away from each other. And if you have 4 things attached, it's 109.5 degrees apart away from each other. Now, figuring out that if you have 2 things, it's 180, kind of makes sense, right? It's 360 degrees of a full circle divided by 2 things gives us 180. Same goes for 3. If we take that same 360 degrees of a circle divided by 3, you get 120, and that part makes sense. Now, where it starts to get weird is if you have 4 things attached, it's not 90 degrees, right? You might think it would be. If you think that, you're thinking in flatland, right? You're thinking in 2 dimensions, right? If you have just a flat molecule and they're spaced out as much as possible, they'd be on like top, bottom, left, and right. But here we have 3 dimensions to work with, right? We can have 3-dimensional molecules. So in 3 dimensions, if you have 4 things attached, the farthest part they can get is 109.5 degrees. Now, you would not be expected to figure that out. That's for all the geometry people to figure out. But what we know is that if we have 4 things attached, we get this shape called a tetrahedral structure, and it has a bond angle of 109.5. Okay? Questions so far? All right. Now let's talk about the effect of lone pairs. So if you add a lone pair, it causes that bond angle to close up a little bit because it repels the bonded pairs. So we start with a linear structure, 180 degrees. And then if you add a lone pair to that linear structure, it repels all those bonded pairs until they squeeze down. That bond angle gets smaller. So it starts at 180 degrees, and then your bond closes a little bit because of that lone pair. Now it's 120. This makes sense so far? All right. So now I just want you to try and reword that. Put that in your own words. How do lone pairs on the central atom affect the shape of a molecule? Go ahead, try and explain. So write a sentence or 2 trying to explain that part. All right, get started.
He doesn't know that I actually know how to like chose water. I can drink a bottle of water and like a couple of seconds. I can. I did that for a girl. And this was like I did. I was like, I like the like got like the bags. So I was like, yo, check this out. And like. And she's like, let's get out of here. She's like, let's get out of here. And I made her drive me home.
All right, let's get our attention up front. Eyes up here, please. All right. So you should have some version of what I'm going to write here. So it decreases the bond angle. So that's one way to phrase it. You could also write it forces the atoms closer together. And again, this is because of VSEPR theory, right? The lone pair of electrons repels the bonded pairs, and that forces the bonded pairs to get closer to each other. Okay? Questions so far? Okay. Now let's go back to Module 3 for a second. Does this slide look familiar? Hopefully. The 4-day weekend made you forget everything. Cool. All right. So just as a reminder, if we want to know whether a bond is polar, nonpolar, or ionic, we can figure out by subtracting electronegativities. So for example, if I was doing like oxygen and fluorine, I could go to my electronegativity sheet that hopefully you pulled up before we started, and I would just take oxygen's electronegativity, subtract fluorine's. Now when I do this, I get about 0.54, and then I just check what range does that fall in. And so I check on my notes doc, and we're between 0.4 and 1.9. So that means I have a polar covalent bond. So when you're trying to figure out whether a bond is polar, you just subtract the two electronegativities. Okay? Now, one thing to note here. This chart helps us figure out bond polarity. Okay? It is not useful to directly figure out molecule polarity. Okay? So we are not going to try and use subtracting electronegativities to figure out molecule polarity. If you want to figure out whether a bond is polar, you can use this chart, but not whether a molecule is polar. Okay? We'll talk about how to figure out whether a molecule is polar next. All right? Now, another reminder, you saw this slide before. These are representations of polar and nonpolar bonds and ionic bonds, right? If it's nonpolar, we share the electrons evenly. If it's polar, they share unevenly, so we have a negative side and a positive side. And then if it's ionic, we have a positive and negative ion, because a full electron got transferred from one to the other. Questions so far? All right, so now let's look at how we can figure this out. So this slide has a lot of text on it. The text is here because if you were absent or if you're trying to review, you can read through it. But right now, you don't need to read through it because I'm just going to summarize it for you in this part here. All right, so let's go through our different representations here. So starting here, let's talk about what this arrow means. So this arrow is showing where the electrons move. If we check our electronegativity sheet, hydrogen has an electronegativity of 2.2. Fluorine has an electronegativity of 3.98. So since fluorine has the higher electronegativity, it's going to pull electrons towards itself. So electrons in this bond are going to move towards fluorine. So we're just showing where electrons move with that arrow. Does that make sense so far? All right. Now, the cross right here, if we cover up the rest of that arrow, what does that cross look like? What mathematical symbol? A plus sign, right? Now that's because if electrons are moving away from hydrogen, its charge is going to be more positive because there's less negatives around it. And the electrons are moving towards fluorine. This is where our negative would be. So that's how we get these signs, right? Now, we have a negative and a positive. Those we can recognize. What's new, though, is this little symbol here, okay? Now, to actually write out this symbol, there's two ways you can think about it. The first is make a D, but then make it curly. Right? That's one way to think about it. Now, the other way to think about drawing this is draw an 8, but just don't finish it. Right? If I finished it, now it's an 8. But if I get rid of that last little part, it's this symbol that we're talking about. Does that make sense so far? All right. Now let's talk about what this symbol actually is. This is the Greek letter delta. Specifically, it's a lowercase delta. Okay? So the Greek alphabet has uppercase and lowercase letters too. Now, we use the Greek alphabet in science and math sometimes because we ran out of Latin, or what are they called? Letters? The normal letters that we use, Phoenician alphabet, that's what it is. Yeah. So we use the Greek letters sometimes. Now this one's just a lowercase delta. Okay? Now, in math and science, if you ever see a lowercase delta, it means partial. Okay? So if you see partial, this just means partial negative and partial positive. So it's not a complete +1 and -1 charge. It's something less than -1. So maybe it's -0.5. And something less than +1, so maybe +0.5. Now the actual numbers don't matter. All we know is just that it's less than a full positive and less than a full negative. Does that make sense so far? Questions? Yes.
So this would be the transfer of electrons that it's showing here, right?
Mm-hmm. Yep. Yeah, we're just showing where the electrons move. So the arrow shows where electrons move, and then these symbols show the effect of that. Right? If electrons moved over here, now there's a partial negative over near the F, and there's a partial positive over near the H. Does that make sense? All right, questions? Anything else before we move on? All right, now we can also represent that here, right? We're showing that there's more negative charge over here and less negative charge over here, right? There's less electrons on this side, more on this side. All right, questions so far? All right, so now, because in this molecule, or sorry, we'll get to the next part in a second, but in this molecule, this is a polar molecule because electrons are moving, right? If we model the electrons as like my body, electrons moved to the left, right? And since my electrons move to the left, that means I end up with a negative and a positive in my molecule. We call that polar. So this molecule has both a polar bond and the molecule itself is polar. Okay? All right, so now let's practice with these symbols for a second. So for each of the molecules down here, I want you to draw on a partial negative and partial positive. So you're drawing your delta minus, delta plus, and then you're also going to draw the arrow that shows where the electrons are moving. You're going to do this for CCl, ON, and HO. Okay? Go ahead and try this out. See if you can do it.
I was like, this is a polar bond, but not a polar bond, because I was like only looking at them when there's two, and I was like, oh, right. Yeah, I'm glad you're aware. If you want to, I would say take a pass. That's just a walk, unless you're so happy. Have you done this problem? Yeah, you know,
It's like the lowest electricity minus the highest.
Not gonna judge you. They look at you and if they look natural, I got this. Yeah, I bet you.
All right, let's get our attention up front. Eyes up here, please. Let's get our attention up front. Eyes up here. Let's stop talking. All right. Let's go ahead and go over this. So if we look at C and Cl, my first step is to check that electronegativity sheet that you should have open from Google Classroom. Carbon has electronegativity of 2.55. Chlorine is 3.16. So because chlorine has that higher electronegativity, we should expect our electrons to travel towards the chlorine. So we draw our arrow, and then draw the little dash on the other side to show the carbon will be positive. Okay? Now, if electrons are moving towards the chlorine, we should expect that the chlorine has a partial negative, and the carbon has a partial positive. So this would be our symbol for CCl. We can do the same thing for O and N. Again, we check our electronegativity sheet. O has an electronegativity of 3.44. N has an electronegativity of 3.04. So electrons are going to travel towards the oxygen, away from the nitrogen. So we have a partial positive on the N, partial negative on the O. Questions so far? All right. Now for H and O, we check our electronegativities. H has electronegativity of 2.20. O has electronegativity of 3.44. So that means O is the higher electronegativity. Electrons are going to move from the H to the O. We have a partial positive on H, partial negative on O. Questions so far? Yeah.
So for nitrogen and oxygen, nitrogen does have, it has less, so it's moving from the one that has less.
Yeah, so remember electronegativity is the strength atoms pull on electrons. So oxygen pulls on its electrons stronger, so it moves towards the oxygen. Make sense?
Yeah.
All right, questions? All right, let's go ahead and continue then. So just a review, reminder, so far we have figured out whether the bond is polar. We have not looked at molecule polarity yet, okay? So now let's actually look at molecule polarity. So this is water, okay? Now water has a bent shape because there's two lone pairs forcing those atoms downwards, closing up that bond, okay? Now if we take water and we label its bond polarities, we have electrons getting moved up towards the oxygen and to the right, and up towards the oxygen and to the left, okay? So now we figured out whether the bonds in water are polar. So we have polar bonds, right? Now let's think about what's going to happen to electrons in this molecule. So if I'm the electron, I'm getting moved up and to the left. And I'm also getting moved up and to the right. So let's model that with my steps. I move up and to the left. I move up and to the right. Now, from where I started, have I moved? Yeah, right? Now, in the left-right direction, I didn't move because I took one step forward left, one step forward right. So I'm just directly in front of where I started. Do y'all agree? So that means the electrons are going to do the same thing. So we can make a combined arrow here, right? We have the electrons that moved up and left, up and right. Those can combine to just make an up arrow. So in this molecule, electrons are just moving up, just like I did when I did my steps. Does that make sense so far? All right. Now, if electrons move up in this molecule, that means that the molecule will have a partial negative at the top of it and partial positives at the bottom. That means that this would be a polar molecule, right? It has a positive side and a negative side. So because it has both positive and negative, we call that polar. Okay? Yes? Mm-hmm. Well, so the molecule itself is neutral, right? Water is a neutral molecule. But inside that neutral molecule, it has one negative end and one positive end. Does that make sense? All right, other questions? Yes?
So when we're looking at this, we need to look at the bonds
Mhm.
and the molecule also. And they're
Yeah.
not the same thing. They can
Yeah.
be different.
And so this is what I was saying before. To figure out molecule polarity, you can't only look at bond polarity. You have to look at bond polarity and the shape, right? Question so far? All right. Now, let's look at an example where you have a polar bond, but non-polar molecule, okay? So this is carbon dioxide. It has two polar bonds. We have electrons getting moved to the right and electrons getting moved to the left. Okay? So let's use my body to model the electrons again. So I'm standing right here. Notice where I'm starting. I have electrons getting moved to the right and electrons getting moved to the left. Have I moved from where I started? No, I'm in exactly the same spot because I moved one step left, one step right. So because the electrons are moving evenly, this would then be a nonpolar molecule, right? So it's a nonpolar molecule that has polar bonds. Does that make sense so far? All right. So then what we see is that in our molecule, we have even movements of electrons, right? We still have negatives and positives, right? But the molecule itself is even, right? We have positive and negative, so we have an even movement of electrons. It's nonpolar, okay? So now I want you to try and practice with this. You're just going to do these first three problems together, three problems first. Then we're going to go over the answers. Then we'll go over the next three. Your goal is to use the bond polarities that are given to you as the red arrows and the molecular shapes that are given to you to try and figure out whether each of these molecules is either polar or nonpolar. Okay? So go ahead and try this out. Use the bond polarity and the shape to try and figure out whether the molecule is polar or not. All right? Go ahead and try it out. See if you can do it. What do y'all think? You got it wrong. So now you know it's not polar. Try to explain why. Okay? How do you know this one? Okay. So what are you thinking about HCl? So which way is the arrow here? Okay, so like if I'm the electron, did I move? So that's polar, right?
So if the attraction or repulsion is the
Now on this one, is there any electrons that are moving? Any arrows showing electrons moving? So if I do the arrow, say, did I move? So I no. Right, so you're just trying to figure out where do the electrons move. Does that make sense? Okay, go. How's it going?
if they're particular equal, if all the things being liquid are equal, that's
Well, so on this one, is this bond polar? So if the bond's not polar, we can't really have a polar bond. So if you only have non-polar bonds, the molecule is also non-polar. I'm not disagreeing with you, I'm just explaining. Does that make sense?
If I were to say I'm going to
You're getting it right. Yeah. So you're just looking at the arrows, right? So if I was this, if I like followed this arrow, and I moved to, did I move? That's polar. If we look at like this example, if I step like forward, or if I step backwards, and then forward and right, and then forward and left, have I moved from your side? Well, so this bond is polar. But we're being asked about the molecule. Okay. All right, let's get our attention up front. Eyes up here. All right, let's go ahead and go over these first three, make sure we understand those, and then you'll try the last three after we reviewed them, okay? So, starting off, for HCl, we have an arrow just pointing to the right. So if I'm acting as these electrons, I move to the right. Did I move? Yeah, I moved to the right. So because I moved, that means we have a polar molecule. All right? Now, for the next one, for Cl2, is this bond polar if we have a bond between Cl and Cl? No, right? We subtract the electronegativities, we get 0, right? So if the bond is not polar, you can't have a polar molecule. So this is where chemistry gets a little confusing, right? If you only have nonpolar bonds, your molecule will be nonpolar. If you have polar bonds, you have to check to see if it's a polar molecule, okay? So this one, since there's no polar bonds, then we get a nonpolar molecule. Yeah. We'll get to an example. Well, so we know it's a, what do you mean check to see if it's a polar bond? Yeah. Well, so if it's a nonpolar bond, the molecule is nonpolar. There's no need to check for that, right? Because if it's only nonpolar bonds, there's no movement of electrons. Does that make sense so far? If you have polar bonds, then you have to check to see if the molecule is also polar. Okay? Other questions? All right, so now let's look at NH3. So on this one, we have electrons getting moved up and to the left, up and to the right, and up and backwards. So in this case, is there any electrons getting moved downwards? No, right? So there's something that's not going to cancel out, right? I would never step backwards if I was acting as those electrons, right? So then this would be a polar molecule. Okay? All right, so now that we've practiced a few, I'm just going to give you a little bit more time, just take about 1 more minute. Try and figure out whether BF3, CH3Cl, and SEH2 are polar or nonpolar. Go ahead and try these out. Well, so, but is this bond polar?
So which way is the direction are they going?
So if the bonds aren't polar,
Is there anything that is like pulling them in so I've got juxtaposed, we have that stuff goes down. Think about what we just looked at. So I'm looking at so our stuff comes up here. Is there anything going in the opposite direction that can't? There isn't. This is polar or not? It is polar. That one is polar.
so in this case, we want to up and left, up and right, up and down. So left and right cancel, up and down cancel.
We're all so smart.
Well, so are these bonds different? So we have H is 2.2, FE is 2.5. So we have no polar bonds, so it's a non-polar.
History.
All right, let's get our attention up front. Eyes up here, please. All right, let's go ahead and go over these last two examples. So, these last two examples, for BF3, we have electrons moving up and to the left, up and to the right, and then moving backwards. So I'm back where I started, right? So we move up to the left, up to the right, and then backwards. There's no net movement of electrons, right? So this molecule, BF3, is nonpolar. It's another example of a molecule that has polar bonds, but is nonpolar. Okay? If we look at CH3Cl, we have electrons getting moved up. That's it. Right? So if they're just moving up, that means this molecule is polar. Okay? Now let's look at the last one. Now for the last one, do you notice that there's no arrows? Yeah? Let's look at why there's no arrows. The electronegativity of H is 2.2. The electronegativity of Se is 2.55. That means my difference in electronegativity is 0.35, which means we fall into the nonpolar covalent range, right? So if you only have nonpolar bonds, that means that you will have a nonpolar molecule. So remember, you have to check to see whether your bonds are polar to begin with. If you only have nonpolar bonds, it's easy. Your molecule is nonpolar. Does that make sense so far? All right. Let's go ahead and continue then. The next thing we're going to be working on is the analysis questions for the polarity lab. So go ahead and get your analysis questions open, and we'll talk about what you're going to do. All right, let's get set up.